welcome. We are day 190. I don't remember. Boat. Nope. 198, 199, not sure. Ooh, 99. Alright, so we're gonna do a little new problem, new topic this time. We'll do some graphs because I want to get some graphs practice. So we did a decent amount of sliding window. You know what a good milestone is to hit 300 before I start school. 300 problems. So yeah, but first let's do graphs. Where's graphs? Graphs. Yeah, let's do these problems. It's good. Oh, no. Let me start this first. No. What is happening? Okay, so we need to first start this so we have a list of problems to grind. So now we're gonna do. Oh wow, do you guys see that, bro? Not a single easy. You know, can we filter by acceptance? Yeah, let's do that. Filter by acceptance and, you know, make our way down, you know? Because I'm gonna go insane. Find the center. I think we saw that before, so let's just start this one. It's been a while since I solved graphs, so I forgot the bullet plate stuff for most of it, so whatever. All paths from source target. Given a directed acyclic graph, DAG of n nodes. Oh, DAG, that's what it stands for. A directed acyclic. I forgot what that means. Acyclic graph. That does not contain any cycles. Okay. Oh, okay. A directed acyclic graph of n nodes labeled from 0 to n minus. Find all possible paths from node 0 to n minus 1 and return them in any order. The graph is given as follows. Graph of I is a list of nodes you can visit from node I. i.e., there is a direct edge from... Okay. Okay. So this one is... Wait. The graph is 0, 1, 2, 3. Where the hell is 0? Okay. All possible paths from node 0 to n minus 1 and return them in any order. So 1... Wait, what? This example doesn't make sense. There are two paths. 0, 1, 2. 0, 1, 3. And 0, 2, 3. Okay, 1 points to... 1 does not point to 2. What the hell? The graph is given as the following. Graph of I is a list of nodes you can visit from node I. Okay, so this is node 0, you can visit 1, 2. Okay, node 1, you can visit just 3. Node 1, you can just... Or 0, 1, 2. Node 1 did that, okay. And 0, 1, 2, 3. Node 3, you can't visit anywhere. Oh, okay. There are two paths, 0, 1, 3, 0, 2, 3. Okay, so Find all possible paths from 0 to n minus 1. So basically to this guy. Oh. So DFS or BFS? So let me build up the kind of I want to build up like a hash map. To make out the thing, and then I can do maybe BFS. Yeah, why can't I do BFS? Let's try that. Maybe BFS. So we go here. I'm gonna go lexicographically the smallest. So we start with here. We add the children 1, 2, then do 1, 3. Okay, first let me build out the I guess map for every I guess I nodes in enumerate graph, right? So I's are index, N is our thing, and it's the list. So we know that I well, this is low-key kind of redundant, not gonna lie, but it is easier. So we're given the source. We can do a Q. I guess we can do DQ while Q. We'll do a we'll do a scene. Right. Some BFS here. Also, I'm gonna add MP0, yeah, cause I'm a G like that. And to start the queue, or I guess we can put the index. Yeah, we can put the index while q dot pop left I is this, right? Then we take that for every n in this, right? So we get 1 and 2. So we add q dot. Wait, well, how do I use DQ again? DQ pop add. Do I just add? Append, yeah. Append do I just n? So 1, 2. Okay, hold on. I dot add or scene dot add I. If n not in scene, then I'm not sure if I'm doing this right, guys. It's been a while since I did graphs. Right, we're doing some BFS here. All paths from source target. I feel like this could be like DFS. Can I see the topics? Okay, thank God. We can do BFS. So we take I. So we added 1 and 2. And we added to the queue, right? So we added to the queue. Okay, I have an idea. Instead of okay, yeah, this is guaranteed to not be, so I don't really care about scene either. Just add it to the queue. Oops, add it to the queue, right? With the append. Hold on, we'll just do res the append. Right? But there's like this sub layer. So we do 1. So we can take this route. I feel like DFS might be better. I can see it like, you know, like, okay, once we finish. But how do I do DFS? Like, I'm missing something here. So we move here. So we go here. 0, 1, 3, 0, 2, 3. Not sure what I'm missing, guys. Help a brother out. 0, 1, 3, 0, 2, 3. Zero, 1, 3, 0, 2, 3. Like 0 goes to a bunch of places. 1, 3, 4. Then hold on. Let me cook. I should have n minus, hold on. I should definitely have n minus 1 here. Right, print. Just give me a second, guys. Just give me a second. It's been a while since I've done graphs, to be honest, so I'm kind of washed. Oh god. Okay, just delete it, I guess. So, a friend is calling me. Hold on. Okay, let me just delete this too. Okay, I guess furry on in range of length of. Oh wait, there's no n. Hold on. N is length of graph minus 1. There's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh shit. Yeah, that's bad. That sucks, bruh. I'm actually throwing right now. This is not that bad. Given a 1, 2, 3, 4. I need to know how many paths there are. So let's go back to our original solution. Trying to think this out again. All right. So I need every layer. Right? So I put in 1, 2. I'll put 1. DFS is low-key the easier one, but I'm curious how BFS would work. Like, we go here. Then we go here. I just need to know where to organize them. That's my biggest thing. How do I organize this? Like, how do I organize like where to put 1 and 3? How would you do that with BFS? I know backtracking, breakfast. I want to do it with BFS because I mess with BFS because it's conceptually easier usually, but or I think the code is easier to conceptualize, but. Okay. The graph is given as follows. 0, 1, 2. 0, 1, 2, 3. 0, 1, 2. 0, 1, 2, 3. Okay. Oh. So you have to put yourself in. Like, okay. 0. Like, I want to do like something like sub, right? And then like, but it's the only problem is I don't know what bucket it would go to. Like, it's like, where do you put 1, 2, or like 1 and 3? Like, okay, so I'm trying to visualize. Okay, we're at 0. We have 2 children, so we have 1 and 2. We put 1 and 2 in the queue, right? So 1 and 2. Let's do this. 1 then 2 is in the queue right now. I guess nothing happens. I guess. Given a directed, I'm just trying to figure out my sub problem. Like, this is a level. I'm trying to see how it could be. Like, how would I know where to put 1? Like, I would have to do some DFS or something. Ooh, how about this? What if we like what if we do this? While true, res or sub dot append, or I guess sub dot append I, dense I right for every and in, right? So that means there's we'll have 1, right? And then MP n dude, I need to see the boilerplate. I have to get some. I need some practice in. Let's see. This is such a really easy solution. I want to see a BFS solution though. Where is BFS? Yeah, Python BFS. Alright, that's such a crappy code, bro. It's not very viewable. Okay, so answer. Yep. Obviously put the first one. Oh yes, the target. I had a feeling we had to do that. If the target is, if the last node in path is the target, add the path to result. Yeah. Exactly. That's what I was thinking of. Because I knew we needed to stop somewhere. Yeah, so we do that. The only problem is how did he do the subarray? So for every explore each neighbor. Okay. So he didn't even make this. There's no point of this. Because yeah. So while Q, obviously we need to put the first element. That, and then I guess target, yeah, target length of graph -1. Okay. What the hell? Okay, so explore each neighbor. So for every I in pop element, starting from this last element, create a copy of the path. Okay. X dot append I. Q dot append X. What? Okay. Let me try to understand this. If I equals target, res dot append I. For every I in, okay, we should not use I then. V. Range of length of nums. Or what am I doing? So like for every in the graph of what pop, okay, so the value, so it's also its children, right? All its neighbors, not children, it's neighbors at the last element, right? Start backwards, cause backwards? Wait, what? There's nothing backwards. Wait, what? Wait, so we go backwards? Create a copy of the path and extend it. Okay. So we pop 0 and we get this one. Okay, I guess it doesn't matter. There's always gonna be 1. Wait, what? Oh, okay. So then X equals V copied X dot append I Q dot append X. Return Wait, I'm kind of confused. Why does this work? Oops, that's bad. Oh, what? Zero? Oh, we checked the last element. Why does this work? Let me see. Start with nothing, the source node. Each element in the queue represents a path traversed so far. Target is that. While the queue is not on, pop a path from the queue. If the last node in the path is equal to the target, append the path to the result list. For each neighbor of the current node, extend the path by appending the neighbor and push the new path back into the queue. The algorithm continues until all possible paths explored. The result list contains. I see. Anyways, alright, that's good enough for today. Good 30 minutes. cut it to the L, but I'm trying to get used to graph screen. Anyways, thanks for watching. I'll see you tomorrow. Peace.